Hello, so in this video we're going to look to using f equals ma that we looked at last time with vectors, right? We also looked previously at how we can represent forces of vectors, right? So what we're going to be doing essentially is saying that f equals ma. We're going to be using this as vectors where f, the force, the resultant force, and a, which is the acceleration, they're both vectors. Okay. So remember, a vector is something with something that has a magnitude, so a length as well as a direction. So it's going to be telling me the physical size of the force or the physical amount of acceleration, so how much it's speeding up or slowing down by, and in what direction. Okay. And so they're both going to be vectors. So that's all we're going to be doing. Okay. So let's have a look at some examples then. So we're told a resultant force of 3I and 8J. So that's the resultant acts upon a particle of mass 0.5. Find the acceleration of the particle in the form Pi and Qj, so in I and J form. So again, we looked at I and J form earlier on in the chapter. If you haven't already seen it in the A level, so you should be familiar with this I and J stuff. So the resultant force F is 3I and 8J, so 3 and 8. We can use columns. We also know the mass is 0.5. So again, F equals ma. Then we can find the acceleration, right? So we can say that if we substitute our values in, then the force as a vector is 3/8 equals 0.5 lots of a. So then we can divide by 0.5 to get a is 1 over 0.5 times the vector 3/8. Well, if we work that out, well, 1 over 0.5 is going to be 2. So that's 2 lots of the vector 3/8. And so that is 6, 16. And there we are. And then in terms of I and J, that's going to be 6I add 16J. And the units again are going to be meters per second, and so there we are. That's the acceleration. So that's the idea essentially. Okay, we're going to be using F equals ma to find the force and acceleration. Then it says in part B to find the magnitude and the bearing of the acceleration. Okay, so again, remember the acceleration we just worked out was 6I and 16J. So the magnitude firstly is the length. Okay. Or then we say the magnitude is these double vertical bars, right? So that's the length. And remember, we worked out the length by squaring all the individual numbers, all the coefficients. So 6 squared and 16 squared. If we work that out, we get 2 root 73. Okay. And so there we are. That's telling me physically the acceleration is 2 root 73 meters per second. Okay. Now, the bearing is again to do with the angle. Again, remember bearings start from a north line. So we want the bearing of the acceleration vector. If we were to draw it, then again, I really advise you do. Well, that's telling me it's going to be 6 across and 16 up, like this. So the force we get, the vector we get joins these start and end points. That's my A. That's my acceleration. Okay. So then it wants the bearing. So the bearing again starts from a north line like this. So we're going to want to find this angle here from the north line to the vector line. So theta here. Now, I think it'd be easier. Well, actually, we can actually work out this angle X in the triangle we've got here, right? We can work out X. Obviously, we've got a right angle triangle. How can we find X in this triangle? Well, we can use SOHCAHTOA, and in particular, we can use tan. So this is the opposite and that's the adjacent side. So therefore tan x is 16 over 6. So the opposite over adjacent. So if we do inverse tan of that, so inverse tan we get 69.44 degrees to 2 decimal places, right? Now that's x. We want theta because that's the bearing, right? The angle from the north line. Well, overall, if we add these two vectors, spot, we get a right angle, so 90. So these two have to add up to 90, theta and x and theta must add up to 90. So therefore, theta is 90 take away x, which is 90. 90 take away this 69.44. If we work that out, theta will be 20.56 degrees to 2 decimal places, okay? But it wants the bearing. So remember, the other key idea with a bearing is it has to always be 3 digits before the decimal point. We've got 2 digits, right, we've got 20. So we need to say the bearing is 0.20 point, let's say 6, if we round it to 1 decimal place. And so there we are, okay? Right, then we've got this example here. So now we're given 3 forces that acts on the particle with mass 3. Find the acceleration. So again, we're going to be using F is ma. F is equal to ma. We know the mass. We know that F is 3, lots of a. But we need to find, well, if we want the acceleration, a, we're going to need to find the force F. But we've got 3 different forces. So how are we going to deal with the force? Well, it has to be the resultant force, remember. So to work out the resultant of all these 3 forces is going to be adding them all up, right? If we add them all up, well, F1 is 2i and 4j, so 2, 4. F2 is minus 5i, 4j, so minus 5, 4. And then F3 is 6i minus 5j, so 6 minus 5. If we add all those up, so add the top and the bottoms, so 2 minus 5 add 6 is 3. And then 4 add 4 minus 5, that's going to be 3 as well. So therefore, that's my resultant force, right? That's F, just the resultant force. So if I substitute that into here, so therefore F is ma, so 3 is equal to 3a. Okay, so that's the resultant force by adding all the vectors. Now I'm substituting the resultant force into here. Okay. Now I want a, so I'm going to divide by 3. So it's going to be a third, right, of 3. Well, that's going to be 1, 1. So that's my acceleration as a vector there. Okay. And by the way, the acceleration, you might not be used to it as a vector. That's telling me, so remember acceleration in general tells me how much I'm speeding up or slowing down by. As a vector, it's telling me how much I'm speeding up or slowing down by vertically and horizontally, okay? So this is telling me the speed is increasing by 1 meters per second every second, upwards and to the right, okay, in that context. So that's all it means as a vector, okay? So it's still pretty much the same idea of if it's speeding up or slowing down, but in particular directions, okay? Right, we've got this question now. So here we're told a boat is modelled as a particle of mass 60, and again we've got these 3 different forces. So it says that given that the boat is accelerating at a rate of 0.8 minus 1.5 as a vector, that's the acceleration, right? So again, if we use F is ma, F is equal to ma, where we've got F equals ma, well the mass is 60, lots of a, so it's going to be times the vector a of 0.8 and minus 1.5. If we work that out, if we times the vector by 60, so 60 times 0.8, that's going to be 48. And 60 times minus 1.5, That's going to be minus 90. So that tells me what the resultant force has to be. But I'm also given all these three forces here. So I can also work out the resultant to be adding these three up, right? These three vectors up, these three forces, right? If I do that, well, F1 is 80/50. F2 is 10p 20q. And F3 is minus 75 and 100. So hopefully you can probably kind of spot how we're going to work out these missing values for P and Q now. Now, if we add them all up as one vector, well, add the top numbers. So that's going to be 5 at 10p. And then the bottom numbers, that's going to be 150 at 20q. Now, that's the resultant force, but due to F is equal to MA, we also saw that F is equal to 48 and minus 90. So we can say that 48 minus 90 is equal to 5 at 10p and 150 at 20q. Because they're both F, right? They're both the resultant forces, okay? And so at that point we can find P and Q because we get these simultaneous equations. So 5 at 10p is equal to 48. And do I have enough room here? No, I'm not going to write it. I'll write it down here. So what we get is the equation 48 equals 5 at 10p. And the other equation, by comparing the bottom, so minus 90 is 150 at 20q. So if we solve for P and Q, well, 10p, if we subtract 5, that's going to be 43. So P is going to be 4.3, right? Here, if we solve for Q, well, 20q, if we subtract by 150, we're going to get minus 240, I believe. Therefore, Q is minus 240 divided by 20, which is minus 12. So that's my value for P and Q there. Okay, so that's literally the whole gist. It's just using F equals MA, right, to find some missing force or acceleration or something like that. Okay. So we've got some exercise questions. So here we're told a particle of mass 8 kilograms is at rest. It's acted on by three forces, F1, F2 and F3. We need to find the magnitude and the direction of the acceleration. So we need to find the acceleration, again, if we use F equal to MA. Well, firstly, the resultant force here, well, F is going to equal all these three forces added together. So that's going to be what F1 is 3 minus 1, F2 is 2 minus 5, and F3 is minus 1, 0. That will be 3 and 2 minus 1, that would be 4. And then minus 1 and minus 5 at 0 is going to be minus 6. So that's my resultant force. So if I use F is equal to MA, so then 4 minus 6 is equal to the M, which is 8. That's the mass. 8 times A. Okay, so 8A for the acceleration. If I divide by 8, then I can say that the acceleration is an eighth lots of 4 minus 6. If I work that out, well, an eighth lots of 4, that is a half, or 0.5. And then an eighth times minus 6 is minus 0.75. So that's my acceleration vector there, okay, in meters per second. But it didn't ask for the acceleration per se, it asked for the magnitude and the direction. So firstly, the magnitude, so that's going to be sort of the length or the magnitude, right? So this is the magnitude, so these two bars, which is the root of the two sort of components squared. So 0.5 squared add minus 0.75 all squared, and so that will be root 13 over 4. Or or as a number. In fact, I'm just going to leave it as in exact form. Okay, that's the magnitude. Now, and by the way, we did look at magnitude before as well, earlier on in the chapter. Again, ideally, hopefully you would have seen stuff to do with vectors here, but we went over it earlier on in the chapter, but that's the magnitude. Then it wants the direction, so that is to do with the angle. Okay, so if I then sort of draw the acceleration vector, right, if I sort of plot it, so this is my acceleration, right? If I plot that then, so 0.5 across, then it's negative 0.75, so it's going to be 0.75 downwards, okay? So 0.5 across, 0.75 downwards. So my vector, if it starts here and ends here, is here. That's my acceleration vector. Okay, so that's just plotting these that vector there. Okay, hopefully with me there. So if it's positive 0.5, so 0.5 across, then negative 0.5, so 0.75 down. Okay, hence I get the vector here. So what's the direction? So what we can say is this angle here. Okay, from the horizontal. So this is the horizontal, right? The horizontal line. So what we can say is, well, to work out theta, well, we can use SOHCAHTOA, right? We can use tan. So it's opposite this 0.75. So tan theta, that's going to be, well, the opposite of 0.75 over the adjacent of 0.5. Does that simplify to anything? 3 over 2. So therefore, theta is inverse tan of 3 over 2, which is 56.31 to 2 decimal places. And so then the direction of the vector, so this acceleration vector here, the direction then, again I said the direction is the angle, so the direction of the vector. Now there's kind of two ways you can do this. The more awkward way is, we could say, if we kind of treat the horizontal as the x-axis, right? So essentially this is x-axis. Well, theta is below the x-axis, it's below the positive x-axis. So I could say the direction of the vector is 56.31 degrees below the positive x-axis. Or, that's very awkward, right? It's like, I have to mention below and the positive x-axis, right? Because otherwise, for example, we could have this this angle here, 56.31, that's above the x-axis. Or it could even be perhaps, it could be here. This could be 56.31 degrees as well, but that would be below the negative x-axis. So you have to be quite specific, right? Alternatively, if you don't want to mess about and faff about with being so specific about where the angle is below what axis, you can just give the bearing. As annoying as bearings can be, they're quite simple to give the direction of something. I can just simply state the bearing. Well, the bearing again is from the north line. Well, then actually it's quite simple really, because we have the first 90 degrees and then theta to get to the vector. So the bearing, we could say, or vector is on the bearing of 90 add 56.31, which is 146.31 degrees. Okay, so we could just give the bearing alternatively, and the bearing is a unique angle in that sense. Okay, so we don't need to be more specific. The bearing just tells me where it is as well. So you can pick your pick your fancy for how you want to specify the direction so where the angle is. Okay, but there we are. And so then in part B, we need to find the time taken for the particle to move a distance of 20 meters. So this is actually SUVAT, right? So remember that. So firstly, we need our distance, our displacement. We're told it has to be 20. U, well, we need an initial velocity. Well, actually, we're told it's at rest. That means it's 0. The speed is 0. So the speed is 0 initially, right? V, I'm not told anything about the velocity after it travelled 20 metres, so I don't care about that. The acceleration. Now, in part A, did we not work out the acceleration, right? Well, we said the acceleration as a vector is 0.5 minus 0.75, but then we worked out the magnitude, right? Which is root 13 over 4. Now that's what we're going to use, okay? We want to use the actual numerical version of the acceleration, right? The actual number, okay? So the physical magnitude of it. So if I do that, I get root 13 over 4. Otherwise, I'd be using vectors with numbers. They don't mix. You'll see, we'll do some questions in a moment where we fall into a problem where vector equals a number. That kind of happens. So we need to make sure it's all consistent. So A has to be a number, like 20 and 0, okay? Right, then T, well, that's what we want to work out, the time taken. Now, if you look at the formula book, if you remember, you see that, well, the equation that does not involve V is S is ut at a half AT squared. So therefore, S is 20, is going to be 0 at a half lots of root 13 over 4 T squared. So then if I simplify this, I'll get 20 is root 13 over 8 T squared. So therefore T squared is going to be 20 divided by root 13 over 8. Does that simplify in any way? No. So then that means T squared is, the only number I get is 44.376 blah blah blah, okay? So therefore T is going to be the root of that. So that's going to be 6.66 seconds to 2 decimal places. So that is the time taken when the particle travels 20 meters with this acceleration. Okay, so there we are. We are told a particle of mass m is acted upon by the forces of 5i and 6j, 2i minus 2j and minus I minus 4j, causing it to accelerate to 7 meters per second. Interesting. Acceleration is a number. Interesting. Not a vector. Okay, well, we're still going to use F is equal to ma. So we need to find the mass m. Okay, well, firstly, again, we've got these 3 forces, so we can calculate the resultant by adding all them up. So 5i and 6j is 5, 6. Added by the other one, 2i minus 2j, so 2 minus 2. Added by this one, minus 1 minus 4. If we add all that up, well, if we add the top numbers, 5 and 2 and minus 1, that's going to be 6. 6 and minus 2 and minus 4, that's going to be 0. Right? Okay, and so if I substitute my answer in, well, 6, 0 is going to be equal to m lots of 7. Now that's really weird. Again, acceleration is not a vector but a number. So this makes no sense, this statement. It's saying a vector equals a number. That is nonsensical. So what we can do in this case, obviously we can't, there's no way we can convert the number into a vector, right? We can't convert the acceleration of 7 into a vector. We don't have enough information there. Well, unless we know the mass, but we want to find the mass. So we'd have no, by itself, we don't have any information to convert the acceleration from a number to a vector. But we know the force of the vector, we can go the other way. We can convert the force into a number by taking the magnitude, okay? So if we take the magnitude of F, so the magnitude of this vector, well, it's going to be the root of the 2 components squared. So 6 squared and 0 squared. That's just 6. Okay? So now that's the actual magnitude of the vector. So now we can substitute this number in, and the equation makes a lot more sense now. So we can say that 6 equals mass times the acceleration of 7. Now that makes more sense. So mass is 6 divided by 7. And there we are. So then as a fact, if I work that out as a decimal, that's 0.86 to 2 decimal places. In kilograms as well, in kilograms. And there we are. Oh, so there we are. So again, we can also work out the magnitude of the vector if we want to use it in numerical form with just numbers, like we used to in the previous video as well. But there we are. Okay, so we've got this question here. So we're told two forces, 2, 5 and PQ act on a particle with mass m. The resultant of the two forces is r. And so we're told that r acts in a direction which is parallel to this vector. We need to get this equation. Very similar to one of the questions I looked at, I think it was 2 videos ago, when we looked at, again, forces as vectors. Very similar question. Anyway, so firstly, it's talking about the resultant of these two. Let's just find it. So the resultant r is these two added together. So 2, 5 add with PQ, which is simply 2 add P, 5 add Q. Okay. Now I'm told that this vector r is basically parallel to this vector here. So that means if r is parallel to 1 minus 2, then remember, think back, if two vectors are parallel, that means they are multiples of each other. So what we can say is that this vector r, so 2 add P, 5 add Q, is a multiple k. So k lots of the other vector, 1 minus 2. And so at that point, it just becomes algebra. So if we multiply by k, we're going to get k and minus 2k. So then 2 add P, 5 add Q equals this. And so then we get these equations. So P add 2 equals k and Q add 5 equals minus 2k. So we need to get to this sort of random equation here. What do you notice? In particular, there's no k in, only P and Q, which means I need to eliminate k from these two equations here. If I call them 1 and 2, these are simultaneous. I need to get rid of k because that's what the final equation they want. It doesn't have any k's in. Well, the easiest way probably is to just literally substitute k here in the first one into the other equation. So I'm going to say sub k equals P add 2 into the other equation. So then I'm going to get Q add 5 equals minus 2k. So minus 2 lots of P add 2. If I expand this, I get minus 2p minus 4. Then if I move everything to one side, I get 2p add q add 9 equals 0. And that's what they want. Great. So there we are. We got there. Then it says in part B now, given also that p is equal to 1 and that capital P, so the particle, moves with an acceleration of magnitude 15 root 5 from the value of m. So we need to find the mass, which is now very similar to the last question we looked at. So if p is equal to 1, firstly let's just deal with that. So if p is equal to 1, well, we can substitute it into this equation here. Then 2p, which is 2 lots of 1, add q add 9 equals 0. So 2 add 9 is 11. So 11 add q is 0, therefore q is minus 11. Okay, so we found P and Q. Well, why do we want to find P and Q? Well, actually, our resultant force is in terms of P and Q, right? So my resultant force, if I substitute that in, so it was P add 2 and Q add 5, right? Yes, there we are. So I've just copied that resultant force. If I then substitute these values in, so P add 2 is going to be 1 add 2. Q add 5 is minus 11 add 5, which goes to 3, then minus 6. And that's my resultant. Now, it wants to find the, if I'm given the acceleration, I want to find the mass. Again, that means I'm going to need to use F is equal to ma. So the acceleration is 15 root 5. So that means F is equal to m times 15 root 5. Now what's the problem here? Well, Well, this is f, right, my resultant. That's a vector. So if I substitute that in, I'm going to get, it would say 3 minus 6 is equal to 15 root 5m. A vector can't just equal a number. That is invalid. So what we're going to do is take the magnitude of this vector here to get it into a number. Okay. So remember, every vector has a magnitude as a length, which is, if we work that out, is going to be the root of 3 squared add minus 6 all squared, which would be 3 root 5. So now I can say that this I can use. So 3 root 5 for the resultant force is going to be m times 15 root 5 for the acceleration. Now, at that point, m is now 3 root 5 divided by 15 root 5, and that goes to a fifth. Okay, so the mass is of 0.2 kilograms. Okay, a fifth is 0.2, and so there we are. That is the value of m. Cool. Okay, I'm going to finish off with this exam question now. Again, this is perfectly doable. Okay, pretty similar to the last few questions. You should be okay with this. But let's go through it. So we're told a particle of mass 0.5 is acted on by 2 forces. Given that the particle is accelerating, this is the acceleration. We need to find k. So again, we're going to use F is equal to ma. Well, firstly, we got 2 forces, so we need the resultant. So F is going to be these 2 numbers. So F1 is minus 4i. So it's going to be minus 4, but there's no j. So it's 0. Okay, so it's just minus 4, 0. Okay, make sure you're comfortable with that. That looks a bit weird, that force. You might expect it to look like this, but there's no j part. So the j part is 0. Okay. So that's the force 1, and the second force is Ki and 2kj, so k and 2k. If we combine that, we get k minus 4 and 2k. There we are. Again, I'm also told the mass is 0.5, so if I substitute this in, I get k minus 4, 2k is 0.5 times the acceleration of 8 root 17. This is a problem, because again, I'm saying a vector equals a number. That cannot happen. So I'm going to need to take the magnitude of this. So the magnitude is going to be the root of, again, we've got k's in there. It looks a bit weird. It might seem a bit undoable, but it is doable, right? It's just a number. K is just a number. We do the exact same process. So the top parts and the bottom parts all squared. So k minus 4 all squared add 2k all squared, right? Right. So if we simplify then inside the root, if we expand the brackets, well, k minus 4 all squared is k squared minus 8k plus 16. Then if we expand 2k all squared, that's going to be 4k squared. If we then simplify inside, we're going to get 5k squared minus 8k plus 16. And there's not much more we can do there. This is what I'm going to use for the force, and this is the length of the magnitude, the size of the force. So if I substitute that into F equals ma, what we're going to get is root 5k squared minus 8k plus 16 equals this here. If I then simplify it, so 0.5 times 8 root 17, that's going to be 4 root 17. So root 5k squared minus 8k plus 16 equals 4 root 17. Okay. So hopefully you're with me up to here. At this point, it's just algebra. This is solving an equation. We can square both sides. Okay, so therefore 5k squared minus 8k plus 16 is equal to 4 root 17 all squared, right? If we work that out on the calculator, that is 272. So if I do, so 5k squared minus 8k plus 16 equals this, then it's just a quadratic equation. So if I subtract by 272, I get 5k squared minus 8k, and then 16 take away 272 equals minus 256 equals 0. If I then do the quadratic formula, so it's going to be 8 plus or minus the root of minus 8 all squared minus 4 lots of 5 lots of minus 256 all over 2 lots of 5. If I work that out, I get k is equal to 8, or k is equal to minus 6.4. Okay, so I've got two values. Which one should I take, if not both of them? Well, actually, look at the question. I'm told that k is positive. So, but k is positive, so we just take the positive answer, right? Therefore, k is just equal to 8, and that is my solution there. Okay, so yeah, that was a challenge question, a bit weirder than normal questions, but again, hopefully it's not too difficult as challenge questions go, right? But hopefully they made sense. But yeah, that's it for this video. So again, the whole idea is we're just applying f is equal to ma to vectors. If we then in this sort of situation where we got a vector equaling a number, we need to take the magnitude of the vector to pull it in number form, if that makes any sense. Okay, but there we are. So I'll see you next time.